Okay, today I want to show you what evidence there is that light is a particle. How did Einstein come up with the idea that light was a particle? Okay. And what it's closely tied to is solar power. Okay, how the solar panels out there work. Okay. Okay, so what they found was that if you shine a bright light at a piece of metal, you can knock electrons off. But when they tried it, it had some strange properties. Because sometimes it knocked the electron off, sometimes it didn't. So I'll try to show you a recreation of what they saw. Okay. So here's a light, it's turned off. I can control which frequency it has by doing the slider. So I can choose which, it goes into the UV and the infrared that we can't see. So I can control that. Okay. It was at 400, right? Okay. And I can control how bright it is by sliding this intensity from 0 to 100%. So right now it's at 0, so the light's off. When I turn the light on, you actually can measure the current that flows down through the wire. This is how a solar panel works. Sunlight hits the silicon, it knocks the electron off and it jumps over here, but that leaves this end as positive because it lost an electron. So these electrons over here want to get there. And the only way they can get back is through the wire. And that's electricity. Electricity is electrons moving through the wire. So I get them to jump by light, and then they want to go back to where they started from. So they got to go through the wire to get there. That's why for electricity to work, you always have to have a complete circuit. Because you always have electrons leaving one place, and you need them to be able to get back. So that's why you have to have a complete circuit for electricity. It's about electrons leaving and electrons coming back. Okay? So as I make this light bulb brighter, the electrons come off and they come flying faster because there's so much energy to knock them off, and then the extra energy gets them to fly faster. Because the higher the light, the more electrons I can get come off. Everybody okay with that? Okay. But they also found that, let's turn this light down a little bit in the middle range, that if I made the wavelength too long, okay, if I made the wavelength too long, see, green still does it. If I make the wavelength too long, the light does not knock the electrons off. In fact, if I make it brighter, that'll be put in more energy. I should knock off some electrons, right? My problem is I don't have enough energy, so if I just turn the light brighter, oh, still didn't knock off any electrons. Well, let's see where exactly the electrons come off. Oh, at 497 I get some. At 502 I get some. At 516 I still get some. At 530 I still get some. 538, 549, I don't get any. So what they found was that there's a specific wavelength, somewhere in the 540 range. I just can't, how do we do this? So 540 doesn't work. 539 does. It has enough energy to get them off, but not get them to move any farther. So they're just barely enough to get them off, off the atom. Okay? So that's what they're trying to explain. Because it doesn't make sense. If I change this brightness, I should be able to make, well, 539 doesn't work. 539 works, 540 doesn't. It doesn't matter how much I change the brightness. The brightness only affects how many come off. It doesn't affect whether it comes off. So each metal required a different color, a different minimum. Oh, that's what I didn't show you. That was one kind of metal. I can change what kind of metal it is. That was sodium. If I change this to copper, they change the color of it, that 591 doesn't work. I'm making it more energetic. That for copper, I have to get it all the way down into the UV, way down here to 220 before it comes off. So it's harder to knock the electrons off of copper than it is to knock the electrons off of sodium. Because that's shorter wave, higher energy. Okay? So copper has a different number than sodium, but it works the same way. If I make it brighter, if I make it dimmer, I get few. Even when I make it really dim, I still get a few. But if I make it too high, make the number too high, it does not matter how bright I make the light. No pieces come off. So each metal required a different color, different minimum energy. What they were trying to explain was why the dimmest of the right color always worked. That as long as I was at 540, as long as light was hitting that sodium, electrons would come off. They wouldn't fly very fast, and there wouldn't be very many of them, but as long as I have a 540, I would still be knocking the electrons off. And if I make the light brighter, I get more electrons off. But no matter no matter how bright I made it, if it was the wrong color, it never worked. So the brightest of the wrong color never worked, but the dimmest of the right color did. And that confused them, because if light's a wave, if one wave isn't enough to take it off, you could hit it with two waves at the same time. That's twice the energy. You should be able to just have the waves all hit at the same time. The brightness was how big the wave was. Amplitude. So if I make the light bright, I should be putting more energy in. I should be knocking off those electrons. It should make a difference. So if light's a wave, this doesn't happen. Okay? Waves don't explain this happening. So what did this mean? The guy who figured it out was Einstein. He wasn't just some Einstein, he was the Einstein. Fact is, this is what he got his Nobel Prize for. We always talk about Einstein in terms of relativity, but he did not get his Nobel Prize for relativity. He got his Nobel Prize for explaining the photoelectric effect. Photo, light, electric, electricity. Light creating electricity. Okay. His only explanation was, the only reason this can happen is if energy comes in particles with different amounts of energy. You got little packets of energy. And if a packet hits an atom, it has enough energy to knock that electron off. Or it doesn't. The packet that shows up either has enough or it doesn't have enough. If it has enough, the electron goes off. If it doesn't have enough energy, it won't knock any off. Now, when I make the light brighter, all I'm doing is putting more particles. So if there's more particles and they have enough energy, it's going to knock off more electrons. When a particle with enough energy hits that atom, the electron goes off. If I have lots of particles with enough energy, I'm going to knock lots of electrons off. If I only have a few particles, a dim light with enough energy, only knock a few electrons off. If they don't have enough energy, if the first one can't knock the electron off, it doesn't come off. No matter how many there are, no matter how bright you make that light. Here's how he knew it had to be this is how he knew it was particles of certain energy. And let me give you an analogy that helps explain why these two pieces make it so it has to be particles with a certain amount of energy. Okay, got an empty basketball court. So you got the basket up there. You hand a 3-year-old a regulation basketball. How many baskets are they going to make? Okay, is the 3-year-old going to be able to get a regulation basketball 10 feet in the air? No, they can't throw it high enough to ever get it up to where the basket's at. So a 3-year-old would never be able to make a basket. Okay, so the second experiment. You got a guy who's 7'7". You hand him the basketball. Is he going to be able to make a basket? Okay, so if I have a tall enough guy, I'm going to make a basket. And if I have a short guy, a little kid, I'm not going to make a basket. Everybody okay with this? Okay, what if I put 50 3-year-olds in a basketball court? How many baskets are going to get made? 0. Okay? But if I put 57'7" guys on the floor, how many baskets are going to be made? A lot. The ones without enough energy are the 3-year-olds. They can't get the ball up. They don't have enough to get the electron to remove from that atom. And no matter how many I have, I'm not going to remove any electrons. If it's got enough energy, it's the 7'7" guy. And the more 7'7" guys I put on the floor, the more baskets I'm going to make. If you can get the ball to 10 feet, you can make a basket. If you can't get the ball to 10 feet, no matter how many people I put out there, I'm not going to get any baskets because you're not allowed to sit on each other's shoulders. And 3-year-olds could never pull it off. So you get how that analogy explains about that it's chunks, and if they're big enough, it happens. The more big chunks you have, the more it happens. Waves can't explain this happening. Okay? So when we said light is a particle, that was the proof that light's a particle. That's the proof that light's a particle. On Tuesday, we'll talk about proof that it's a wave. You've already seen the proof. You just didn't know that I was proving to you that it was a wave. Okay. But that's where I wanted to stop today. So, didn't want to have you do any heavy thinking, so I gave you a little light practice. But anybody who's done weights says, hey, when the practice is light, what you're supposed to do is lots of reps, right? But you're not allowed to talk about weightlifting that way. Now, you do max some days, but you don't, the other time you do lots of reps, right? So, okay, I have not set it up so it's got the give and find formula substitute. But guess what you should do, in your head at least? Given, find, formula, before you start writing stuff down. Do it in your head. I did, there's a couple more because there's not enough. Nah, it's not that bad.